Welcome back. Today I'm going to be looking at a Kalman filter again. It's a real-time Kalman filter demo, but this time on the ESP32 using the Arduino language. We could of course use Python or some other language. We're going to use what's called sensor fusion. I'll explain that in a minute. So this is the sort of thing that if you're trying to measure the tilt angle of something, maybe for a quadcopter or a Segway, and you're trying to keep the thing balanced. It's like a balancing exercise, or it could be for an aircraft or whatever, but not for this particular device. This is the MPU 6050, which I'm sure a lot of you have seen. This is the actual chips on here. This is a board that you can buy, which is already made up, so you don't have to do too much, and you only need about 4 of the pins there. It runs off 3.3 volts. Sell for a couple of dollars, and that's going to be connected to the ESP32. So I've done that over here, and there's just it's connected through the I2C. I believe that's the Philips interface. This is the ESP32, and that's the MPU 6050. I've got the oscilloscope leads running off it, and I'll explain in a minute, but basically the scope here is just a waveform, and if you look at, you read the what it says there, it's reading 50.00 Hertz. That's the sampling rate that I've set the whole thing up for to acquire the data, and that's pretty accurate. So let's just have a look at the theory first to see what we're doing. Now there is another lecture I've given online about the Kalman filter, which is a little bit more detail. Some of this comes from my book, which was published last year, January last year, 2020. It's called Feedback, published by Springer. So this is the MPU 6050 that I've just shown you. It runs off 3.3 or 5 volts, and it's very easy to connect up. There's only 4 pins, and this is the ESP32. It's pretty cheap as well. It's New Zealand dollars, about anything up to $6 New Zealand. It's only a few US dollars, depending on the quantity you buy them in. Come in different number of pins. This board, the actual device itself is here, and this is a little board that it comes with. If you need that, it's handy to use that. What this small device here gives us off is, it gives us off 3-axis acceleration and 3-axis velocity from a gyro. So the gyro gives velocity, and acceleration comes from accelerometers. It's in 3 axis though, so we've got to be careful how we get this. And how I define this here is that this is pitch, that angle, and this is roll, okay, in that direction. This would be yaw, but unfortunately it can't work out yaw. You need a compass for that. Yes, I see a lot of people trying to do this online, but you can't do it without an extra different chip. There's a more sophisticated one than this that has got a compass, and then you have to set that up in a special way. This one hasn't got the compass, so we can only do pitch and roll. I'm only going to do pitch here though, however, to give you an example of how a Kalman filter works. But there is another way you can use, rather than a Kalman filter, you can use what's called a complementary filter, which I have used in the past. And it's because accelerometers give accurate readings at low frequencies and gyros at high frequencies. There's a necessity really to combine the two so that you get the best of both worlds. Now, we can of course just use the accelerometer readings, and I can show you what they look like. They're okay, but they're a little bit noisy and a bit sensitive, too sensitive if anything. Whereas the accelerometer, the gyro readings will give you angular velocity. So to get to position from velocity, you need to integrate the gyro reading. Now, integrating anything is a bit of a pain, because certainly in an open loop system, because any small amount of DC that gets into it, and it just gives you huge errors. So integration in an open loop form isn't good. Likewise, if you had acceleration and you wanted position, you might think I just need to accelerate to integrate twice, but again, that's even worse still. But here we don't actually have to integrate our accelerometer readings. When you think of it, the confusing thing is when you look at the accelerometer, you think I need to integrate it twice to get position, but you don't actually, because it's the direction that the acceleration's going in that we actually use, and we use the arctan function for this. So if you low pass one of them, say the accelerometer one, it's got to be, and you high pass the other one because that's the gyro one is good at high frequencies, and then you combine the two, you basically just add them. It means that the filter's got to sort of add up to one when you know the low pass and the high pass one, and it's a very simple way of doing it, and there is some kind of success in doing it that way. But it's not the method I'm going to use here. Instead, I'm going to use a Kalman filter. It's a little bit more scientific. This is the block diagram of a continuous time Kalman filter. It's got feedback around it. You should understand state space in order to understand this, and how systems represented in state space. An integrator, that's the A matrix of a continuous time state space system. X dot equals AX was BU, Y equals CX. The observations, that's the, in this case this is going to be multivariable, because we've got accelerometer reading and the gyro reading coming in here, so that would be actually a vector here, and what we get out is a vector which is state estimate, and that will be position and velocity. Now, position and velocity actually is a good thing for control systems, because they're great for feedback position to control the tilt or whatever angle, and velocity is stabilization. It's the first derivative of position, so it's like proportional plus derivative control of your feedback the states when you've got position and velocity. This bit here, the B term isn't really used here at all, and we're just using it in the filtering mode. That is in the original theory of the Kalman filter is needed. But if you're controlling something around 0, which is what I'm doing, I'm actually not doing any control, I'm just actually doing the filtering, but that's really not needed, so we only need this part of the Kalman filter. Now, this is it from my book, and it's not the only way to do it, but these are the equations of motion. That's to say Newton's laws in angular form. This is in state space form, so this is like X dot equals AX plus BU. You see there's two inputs, and they're both noise terms, modelled as white noise. This is the A matrix. There's a negative there because due to gravity going the other direction. This is just the identity matrix. I call that, you can call that D here, but to avoid confusion with the B matrix. And there's two outputs, again a vector, y equals CX. C is also the identity matrix, and to that there's measurement noise here, VG and VA, and which gets added. This is standard sort of equations for state space, but just applied to the Newton's laws. So the first thing we need to do really is get them into discrete time for a particular sampling rate. Now, the way that the Arduino works and the way this device works is it's not exactly galloping along in terms of measurements. I don't mean the ESP32, but the 6050, and it's quite a slow device really, the way it's been set up with the libraries. I'm just using the libraries. And so I'm quite restrictive for my sampling rate. I've had to make it 100 Hertz, but 100 Hertz is okay for many things that are very slow, and you know, like a Segway, sampling rate of 100 Hertz is okay, because the bandwidth of the control system around that is maybe only a few hertz. It's fast enough to keep it up. upright. When you discretize these, and again that's you can read about that in my book or look online, how to convert from continuous time to discrete time state space, you end up with these matrices here. In fact, I think this may even be in Wikipedia if you have a look. TS is the sampling interval, which would be 1 over 100, because it's 100 Hertz in this case. So it has to correspond, if you're doing it in real time anyway, to the real sample rate, otherwise it doesn't make any sense. If you're simulating, just on a Matlab or something, you could just put 1 in there for unity sampling, and then everything's respect to unity sampling. Notice the C matrix here is just identity, and these are the, I call this the F matrix, and this I think I've called the D matrix. You could call it G if you wanted to, sometimes it's called that. Oh, it's called G here, I see, but in my program I've called it D. And that's the discrete version. And the Kalman filter is just this iteration here. The hat meaning the estimate, time k plus 1 given k is actually a predictor for one step, is fx hat k given k minus 1 plus this matrix k, which we've got to find, times e, which is an error, and it's a vector, e is a vector error in this case, y minus h x hat, that's the previous estimate. And we just iterate that round actually, or we can do it in a simpler form, which I'm going to implement it. We don't actually need the error, we can implement it in closed loop form. So these are the equations. They're called the Riccati equation to find the Kalman gain matrix here. We also need this other thing, which is the error covariance matrix. So you need to iterate that round and round and round until it converges in steady state. Of course, if the matrices were changing with time, the Kalman filter can take account of that, and then you'd have to iterate that in real time, and it would track it, but you'd have to know the system varying in time. And to do that, you often use an extended Kalman filter, but that's not often guaranteed to converge, so there's problems there. But in this particular case, everything's sort of static, and we can iterate this equation and find, beforehand we can find the gain matrix on Matlab, which I'll show you in a minute. We need to know various things. Q here is a matrix of the noise terms coming into the device, and R, where is it? Oh yeah, R here is the measurement noise covariance matrix. So these are also necessary for the calculation. In Matlab it's just a one-line command to do it, but if you wanted to, you can iterate these round in Matlab, and in my book I do this for a simpler case anyway, and you end up of course with the same answer as Matlab anyway. So what's important here is that the accelerometer actually gives you out the angle straight away. So you might think, well, what am I even bothering for? If I can read the accelerometer equations, I can get the pitch and the roll straight off. I just need an arctan function here, that's the x reading of acceleration, that's the z here, and that's the y, and that gives me the pitch angle, and I can do the same for the roll, but that's y and that's x this time. It's sort of reversed. The trouble with that is a little bit noisy, as I explained, good at low frequencies, but not for faster tracking. And I'll show you a comparison of the two. So the accelerometer, the reading that we're getting, it isn't actually acceleration, it's an angle, so we've got to be careful there as well. Although of course it does give off acceleration, but we're working out the direction at which that acceleration occurs, which is a little bit different. So the definition here is roll, pitch and yaw, depending on which way it's orientated. The yaw, as I say, we can't get because you need a compass, but we can get roll and pitch with a simple device. So the Matlab code, so define the sampling frequency as, oh, I can't write on that, that's just 100 Hertz. Then there's a sampling interval, there's 1 over that, and then just sample for 200.5 points. I don't really need that actually, that was for different simulation. Then I define my F matrix, which is like the discrete A matrix, so my sampling interval, and my observation matrix, which is the identity matrix. And I'm just making the process noise covariance unity and referencing with respect to that. So I'm making the measurement noise covariance is 10 to the minus 2. It's just arbitrarily at the moment. Initializing the error covariance matrix, and I need another matrix which is zeros for the, it's just for the Matlab program to run on. And there's the command and the one-lined function, if you like, in Matlab. Sorry, that's not it. Where is it? Yeah, here. Kst kd kp2 equals Kalman, and that's the system Q and R, which is the noise covariances. That's the defining the system up here. You're converting it from, or defining it in state space from the matrices. Okay, and then display KD. That's the Kalman gain matrix, and I use that in the program. And then I can find a closed loop Kalman filter transfer function if I want to. And really, it isn't technically a Kalman filter. This is a Wiener filter because it's a steady state Kalman filter. However, Wiener never actually looked at state space. He only looked at transfer functions, and he never even looked at discrete time. That was Kolmogorov, another engineer who looked at that. Wiener was a mathematician. And by the way, the pronunciation of, because people have corrected me in the past, of Norbert Wiener is actually Wiener in the sense that that's how he pronounced his name. It wasn't Wiener, which is the German term. It was translation. It was Wiener was how he liked his name to be told. And I know that because a colleague of mine, old friend, worked with him way back in the 1960s. When he was in America. So that's how he pronounced his name. So it is really a steady state Kalman filter is actually a Wiener filter, and I'll show you can get the transfer functions for them for that particular sampling rate. So the Arduino stuff I'll come to in a second. Just wanted to say this is my other book which is coming out this year, Rudiments of Signal Processing and Systems. That'll be out hopefully in 2021. So back to the, here's the Matlab code here, and I'm just going to run it. And you'll see it gives out, there's the matrix of gains, if you can see that. Yeah, 0.0955 minus 0.0055 and so on. And we can also find the transfer functions because there's two, because it's multivariable, and it works out these are the transfer functions of the Kalman filter. So you could actually implement them as well rather than implementing the in state space format. That's another alternative. You should get exactly the same answer in this case. That's the closed loop A matrix or F matrix here. You can work out its eigenvalues, and you'll see that its eigenvalues are the poles of the closed loop Kalman filter, which are also the same as the roots of this polynomial here. So let's go to the Arduino and fire it up. So I'm just going to, here it is here. So a lot of this I took from the random nerd tutorials on these websites here, and they're pretty good. So I've obviously acknowledged that, but I noticed they didn't put the calculations with the arctan in there, so they were just giving out the raw accelerometer and gyro data, and I really wanted the angle as well, so I had to stick that in as well, plus the Kalman filter, plus I use interrupts for the sampling frequency. You'll see here the Kalman gain. I'll just put my glasses on so I can see what I'm doing. yeah, here the Kalman gain in terms of the, because we don't have matrices here, we just have constants K11, K12, K21, K22, and this is the interrupt service routine here for the timer. I've set all that up to 10,000 microseconds, which is 100 Hertz. And this is just me setting up the F matrix for the Kalman filter. And then I've just typed in the K values I got from Matlab, and these initial state estimates. And if we go down to the actual calculations, you see that you have to have the square root of the z squared plus x is plus y squared part and the arctan function to get the angle. Then the Kalman filter itself isn't too complicated because it's a steady state Kalman filter. It's just the matrix form. I've had to put it into longhand form. X hat 1k equals fc11 times x hat 1k minus 1 plus and so on, where S1 and S2 are the observations. In this case it's the acceleration and gyro readings. And I just going to use, I mean, I know it's very crude, but I'm just going to use the serial print, which means I can actually use the serial plotter to put the two values. So what I'm going to plot is the raw accelerometer angle and the Kalman filtered one. And here it is here. I'm just going to take the this off the scope so that I can show you. Oh, so it's sort of in front of me now. So the red one is the Kalman filter output. You see the smoother one, and the so I sort of shake it about a bit. And the blue one is the accelerometer reading as it comes out. And as I tilt it, you see it's going up, down, measuring the angle. Okay, so this is using, so this is sensor fusion. It's taking account of the accelerometer as well. The Kalman filter estimate is at least. The blue one is just the accelerometer readings on their own. Now, as I said, the accelerometer doesn't need to be integrated because it's a direction, so it's found from the arctan function. You don't integrate acceleration twice to get that angle. You just work out an arctan function, and there it is, really. Real-time Kalman filter, not exactly super fast, but it's running at the correct sampling rate. You saw earlier on the scope, it was reading 50 Hertz, which corresponds to 100 Hertz sampling rate, actually, the way I've done it. Okay. So you see, again, just leaving it, just holding it here, the blue is much more sort of noisy than the red, because my hand's shaking a tiny bit. Okay, so there it is, a real-time Kalman filter using the ESP32 and the MPU 6050. Thank you very much.